All right, ladies and gentlemen, so today we're going to jump into chapter 5.8, growth and decay. Okay. Yesterday we kind of did growth with compound interest and continuous interest. When we put money into an account, we wanted to grow bigger and bigger. Well, that's kind of like what we have here with cell growth. So with cell growth, I have n of t equals n sub 0 e to the kt. This is what we call subscript. Think of a submarine. When you have a submarine, it goes below the surface. So this is below the n. So n sub 0 is what that's called. N sub 0 is the original amount where we're starting. Okay. Well, that's kind of like our principal yesterday. Principal is the initial amount that we start with. And then we have E, and we have E, and then this is to the KT, and this is to the RT power. Okay, so this is the formula that we used yesterday, the PERT shampoo formula, and this is the formula that we're using today. They're the same. They just have different letters for A and P, and then K is your rate. Well, if it's growing, so if it's growing, it's getting larger, it's going to be a positive number. All right, and if I take a look, radioactive decay, you guys should know what decay means. When something dies, it eventually becomes dust, right? It becomes less and less of itself until it becomes part of the earth. Well, that's decay. So they're using the formula A equals A sub 0 e to the KT. A sub 0 now is the original amount. K is the constant. Again, K is the rate. And if it's decaying, then that's going to be a negative number. That percentage is going to be negative because it's becoming less and less over time. So if you're pretty good with the PERT shampoo formula from yesterday with continuous interest, you'll be just fine with these two formulas. They're identical. They're just switching N and N's, A's and A's for A and P, or vice versa. Okay, and the K is the same thing as R, your rate. We'll talk more about Newton's law of cooling, which is pretty nice if you are looking to, investigate a crime. Maybe somebody's been killed or something, and you're trying to investigate when was this person, deceased, or when did this person get killed. So maybe you're in forensics and you're trying to figure out like a crime or something. Or maybe you're eating some pizza and you don't want to burn the roof of your mouth, and you got to figure out at what point is it safe to eat this pizza right out of the oven. Okay, because nobody wants the skin on the top of the roof of their mouth to be burnt. That's awful. Okay. All right, so ladies and gentlemen, let's dive in. Here we go, example 1. Okay. Says here, I have a sample of bacteria and it grows according to the formula N of T equals 100 E to the KT 4.045 T, where N is measured in grams and T is in days. Okay, so this is going from that growth formula. I'll write the growth formula right underneath. Okay. So part A says determine the number of bacteria at T equals 0. Okay, well, they're basically asking us what N of 0 is. What's your initial amount? Now, if you didn't know that they're asking what N of 0 is, what's the number in front of E, technically you could just use the formula up here and plug and chug. So if you didn't know they were looking for N of 0, you could just plug in 0. Well, what we get here is 100. E, 0.045 times 0 is 0. Anything raised to the 0 power is 1. And 1 times 100 is just 100. So you didn't have to do any of that work. If you knew the initial amount at time 0, you could have just said right away 100 grams and been done. Okay, if you didn't know that, then you got to plug in the 0 and eventually you're going to get 100 either way. Okay. So it takes a look, and next part, and this is very similar to what you're going to see on my math lab for homework, is they're going to walk you through some different questions here, 4 or 5 questions. It says, what is the growth rate of the bacteria population? So basically, they're just asking you for the K value. So this is where you're going up to your formula and you're identifying what K is. So take a look. Tell me what number is K for you guys. What do you think? Duncan, Lisa, Aiden, Rach, Andrew, Leo, what do you guys see for K?
0.045.
Yeah, so 0.045 is your rate, your growth rate. Okay, if you want to write that as a decimal, you can. For me, would be okay. You got to see what my math lab wants. If they want the percentage, move that decimal place over to the right. So it's 4.5%. Okay. So I'm okay if this was a quiz or test in my class, you know, taking it in class normally without my math lab, I don't care which one you give. I would accept either. You got to see what my math lab will accept. Okay. All right, so that's pretty easy. That's just identifying your initial amount for part A and identifying your growth rate for part B. Okay. Really no work needed for A and B. When I take a look at C, it says, what's the population after 5 days? Again, that's your T value, okay? So they want you to find N of 5. So plug it in, plug it in. I got 100e to the 0.045 t, where t is 5. And I plug that in my calc. So get your calculators out. Again, you should be verifying that you know how to punch this stuff in. Okay. So I type it in. Remember, E is right here next to the 4. You guys take a look. That's natural log. But press second natural log. That's e to the power. So that's e to the power of 0.045 times 5. Press enter. And after 5 days, it went from 100 grams up to 125.2 grams. Okay, so final answer. So they might ask now what happens in 10 days and what happens in 15. We're just replacing the t value. Plug in and chug in. Okay. All right, so the next one says when. Well, anytime I see when or how long, it's just like example 3 from yesterday. They want us to find the exponent t. Okay, so when we're doing D and E, we got to find t. When will the bacteria population reach 150 grams? Okay, well, that's my N value. Okay, so I go up to my formula, N of t. In this case, 150. That's my N of t value. That equals a hundo. E to the 0.045 t. We want to solve for t now. So I got 150 equals 100 e to the 0.045 t. And now I just want to solve for t. Well, what's the first thing we got to do? What do we got to do to solve for t? What do you guys think? Hayden, what do you think? Wade, Janelle, Herbie, what do you think? Herbie? Do we have a Herbie in this class? How do we, what's the first step we got to do?
Don't you have to log it?
We will log in a second, but that's going to be the next step. So good guess. What do you think? Ramen, what do you think? McKenna, what do you guys think? Shay, Connor. We are going to log both sides, but not yet. This 100 is in the way. How do we move this 100?
Divide it over.
Yeah, buddy. Go ahead and divide over. That's the first step. This guy cancels, and now I got 150 divided by 100 is 1.5. And that equals E to the 0.045 t. Now, my little trick for this one is, this thing is so high I can't reach it. unless I step on a log. And in class, I have this big old log, the tree stump, and I physically step on it and I act like I'm reaching on a top shelf, and now I step on the log and I bring that thing down. And if you log one side, you want to log the other. Now, this is the reason, one of the reasons why I choose natural logs, okay, in this step. So I've got the natural log of 1.5 equals, now I bring this guy down at 0.045t, and then times the natural log of e. Well, the natural log of e is a special log, okay? So if you don't remember, natural log has a base of e. So this is really log of e base e. Well, the log of e base e is 1. So this is another reason why Mr. Gotsch uses natural logs, is because I know this is 1. So once I bring this guy down, I don't write natural log of e because I know it's 1, and 1 times 0.045t is just 0.045t. You don't need the natural log of e anymore. Okay? That's, again, another little trick. That's why I use natural logs as opposed to common logs. Last step, solve for t. I'm going to divide over 0.045. And I get t equals, and I'll write this out for notes, natural log of 1.5 divided by 0.045, which is, let's see how many days it takes. So natural log 1.5, close that parenthesis, and then divide by 0.045. And it takes me just over 9 days, 9.01. I'm going to round to 2 decimal places. You got to see what my math lab wants. Tenths, hundredths, so I rounded to the hundredth spot. So I got 9.01 days it takes to go from 100 grams up to 150 grams. So just over 9 days. Okay.
Will that unit always be days?
Well, it'll describe it in the original question. Okay, so this one said N is in grams. It could be in ounces or pounds or something. And then T's in days. It could be hours, minutes. It just depends. It's a good question.
Okay.
Okay. My guess is for my math lab, you just have to punch in the number. They don't care about the units, but I'm just putting it in there for you. All right. So when I take a look, question E is almost identical to this one, okay? And what you punch in is very similar to your calculator, but in this case it says when, so what's T? Will the bacteria of the population double? Okay, well, they don't blatantly tell you what N is. You got to know what N is, okay? For you to know what N is, if it's doubling, you got to know what you started at. Well, where did we start? What's our initial amount? What's N sub 0 versus what's doubling that? So that's where you have to look back at part A, and we found N sub 0 is what, a hundo? So if it says double, I got to know that's 200. So again, I know N sub 0 is a hundo, so I double it. If it said triple, when will the bacteria population triple, then N would be 300. If it said quadruple, then it would be 400, okay? But it's based on what N sub 0 is. So whatever N sub 0 is, double it, triple it, quadruple it, what have you. Okay, so if that's just 50, double would be 100. Okay, hopefully that makes sense. So I pluggy chuggy. N is 2 hundo. N sub 0 is 100. E to the 0.045t. And then we do the exact same thing. We divide over. This cancels. 200 divided by 100 should be 2 because it's doubled. E to the 0.045t. Again, this is where we natural log both sides, so we can bring this guy down. I've got the natural log of 2 equals 0.045t. Natural log of E, if you include it, that's fine. If you divide it over, that's fine. But natural log of E is 1. You don't need it anymore. Okay. Last thing I would divide, and you'll see that when I punch this in, it's very similar to what I just had. The only difference is instead of natural log of 1.5, I have natural log of 2. If it was triple, it'd be the natural log of 3 divided by your rate. Okay. So I'll punch that in real quick. How long does it take? Natural log of 2 divided by 0.045. How long does it take to double? And takes me about 15.4 days to double. Okay, so about 15.4 days. If it was triple, nice thing is I have this already set up. I'll just go in here. If it was triple, that's going to be a 3. It'd take 24 days to triple. If it was quadruple, I'd go in there and change that to a 4. It'd take 30.8 days to quadruple. Okay. Good stuff. Not too bad. So that's kind of the setup of the first few questions. They're going to give you the equation, and then you guys start answering some questions about it. And I've given you 5 different examples that you could see. Okay. Alrighty, let's move on. Any questions? Give me a thumb. Where are we at here, gang? Give me a thumb. We have thumbs up, thumb sideways, thumbs up, sideways, up. Okay. Hope we're writing this stuff down. I just looked in the vestibule, guys. I still have tons of packets in there. If you're going out to lunch today, grab a packet. Okay, or print this stuff off. Oh, man. All right, so very similar to our last question, but it doesn't or isn't going to blatantly tell us what our K value is. So this is a little bit tougher. So on the OMG scale, on the oh my gosh scale, I would give this about an 8. Okay, so number 2 is the toughie. Okay, so pay attention. All right, so it has here, says traces of a burned wood along the ancient stone tools of an archaeological dig were found to contain approximately 1.67% of the original amount of carbon-14. And you're like, what did he just talk about? Okay, so first thing is you got to know a little bit about being an archaeologist and being a scientist and understanding decay. Okay, all living things, if you didn't know, all living things have carbon-14 in them. Okay, and then when we die, we start at 100%, and when we die, our carbon-14 starts decaying, which means it gets less and less. Okay, you guys heard this in chemistry and biology class, right? You guys have heard carbon-14 dating or carbon dating. Okay, so this is basically ways for scientists to discover or identify how long ago this artifact was on Earth. Okay, they use their carbon scoring or carbon dating to figure that out. Okay, not carbon scoring, that's from Star Wars. Carbon dating. So what we did is we're this an archaeologist, maybe we're Indiana Jones or something, and we found this artifact and we had it analyzed, and it said there's 1.67% of its carbon-14 left. Okay, well, we want to know when this tree was cut down and burned. We want to know when this looks like it's a piece of wood that was attached to a stone tool. So maybe it was an axe or a hammer or something. We want to know how long ago this tree was on Earth before it was cut down and burned, okay, and turned into a tool. Well, it says here the half-life of carbon-14 for you go from 100% of carbon-14 down to half of it. So half-life, 50%. It takes carbon-14 about 5,600 years to go from 100% down to 50%. Okay, so you're living, you have 100%, and then when you die, you start losing your carbon-14. Well, it takes you 5,600 years to get down to 50% of your carbon-14. Okay, well, we got to figure out first is what is the decay rate. We got to find the decay rate of carbon-14. They don't blatantly tell us, hey, it's 0.045 like in the last question. So the first thing we got to do is we got to find that. So this is a two-step question. I'm going to do step 1 over here and step 2 over here. So first we got to find their decay rate. You can use any values you want. I'm going to use what they use on the front, where it's A equals A sub 0 e to the kt. And that's our decay rate formula. If you want to use N's, you can. If you want to use A's because your name's Andrew. If you want to use L's because your name's Leo. Or R's because you're a pirate or your name's Rachel. Whatever you want. It doesn't matter. Okay. But I'm going to use this information about the half-life, and it takes 5,600 years. Okay? So again, first use half-life so that we can find the K. The idea is, well, if I'm going to find out when this thing was cut down, I need to find T. Well, if I can't find T unless I know K. So there's two variables here. Okay, so I need to know one of them to find the other one, is the idea. All right, so I started at 100%. I'm down to 50% half-life, right? E, K, I don't know what the decay rate of carbon-14 is. I'm going to find that out. And I do know that it takes 5,600 years to get down to 50. Okay? So far, so good. So this is 100% carbon-14. That's where I started. Half-life, I'm down to half of that, 50. Okay? Now, if it was me, I would probably just do a half over here, but I think this helps you guys visualize what's going to happen. We're going to divide over, and then 50 divided by 100 is 0.5. And that equals, this guy cancels, that equals E to the 5,600K, or K times 5,600, whatever you want to do. I'm going to natural log both sides, because I want to get this K down. It's up in the exponents. I can't reach it unless I log both sides, step on a log, and bring it down. So I got the natural log of 0.5 equals 5,600K. Now I'm going to divide it over. And I get K equals this guy. Or if I want to put it in my calculator, natural log of 0.5, close it. And then I'm going to divide that by 5,600. Okay. Now again, I do get a negative because it is a decay rate. That's normal. And this one says it's negative 1.23776 e to the negative fourth. Remember, that's scientific notation. Okay. I'll write it like this. Negative 1.238 times 10 to the negative fourth. If you want to make that negative 0.0001238, you can do that as well. Either one of those. You got to see what my math lab wants if they're asking for the decay rate. But they're really not. They're asking you, when was the tree cut down and burned? This is the second part. Okay, we're going to use this K value now. When T equals question mark. So now we're trying to find the T value when A is 1.67%. How long has this been on Earth? Well, I start at 100%, right? My carbon-14. When I found this artifact, it was down to 1.67% of carbon-14. E is E. K is what we just found. That's our decay rate. So use this guy here. You can use the natural log of 0.5 over 5,600. You can use this decimal here. That'd be fine. It's kind of whatever you want. And then we're trying to solve for T. Okay, so any questions on my setup so far? We had to find the K value so that we can find the T value. You can't find when this all happened until you know your decay rate. The nice thing is this is the decay rate for carbon-14. You'll never really need to solve for this guy again, okay? Because it never changes. It'll be the same thing for carbon-14. That's what's nice if you have your notes on a quiz or test, you just use them. 1.67 divided by a hundo. Go ahead and move that decimal place over 2 spots. That'd be 0.00167. Oh, I think I have an extra 0 in there. Make that a big dot. So 0.0167, sorry. So move it 1, 2. So point, that's a big decimal. And then I have E, and then 2, either the natural log of 0.5 or you can use the decimal, whatever you guys, let's use the decimal if that helps you guys. Kind of whatever you want to do, either or. Well, I want to get this T, I want to solve for T. I'm going to step on a log now, and now I can bring this guy down. So now I have the natural log of 0.0167 equals negative 0.0001238 T. Natural log of E, you don't need it because it's 1. It just disappears. And now my last step, I divide this guy over. And then type that into your calculator. So I'm out of room, I'm just using an arrow, I'm typing that in. Calculator says I have the natural log of 0.0167, close it, divided by this decimal. This is where it's really nice when you have a TI-84, you can just go up and highlight it and press enter, and it cut and paste that whole thing in there for you. Okay, and then there we go. So we get 33,062.44444 years. So that tree was cut and burned down 33,062.44 years ago. Holy cow, that's a long time. Probably prehistoric age. So applications, man, maybe you're going to be a scientist and you're trying to identify how long ago this artifact has been on Earth. Well, growth and decay method. This is an example of decay, how long you can find. Okay. All right, all right. Do we have any questions, ladies and gentlemen? All right, so I'm going to finish up real quick with example 3. If you guys have no questions. It says here we have a pizza is baked at 100 degrees Celsius and then allowed to cool in a room where the temperature is 30 degrees Celsius. Temperature of the pizza is 80 degrees Celsius after 5 minutes. At what time can you begin eating the pizza? Well, for us to be able to answer this question, we got to know a little bit about Newton's law of cooling. So if you look at the front page, we have our formula there. Okay, so Newton's law of cooling looks like this. U of T, okay, that's the temperature of your object after a certain amount of time, okay? That equals big T. That's the temperature of the surrounding area. So if you're in a room and your object, your piece of pizza is sitting at room temperature, it's the temperature of the room, or room temp, okay? Typically like 70 degrees, okay? This is in Celsius, so we must be in Europe or something. Plus U sub zero, that's the initial amount of your object. So in our case, our pizza when it comes right out of the oven. Minus big T, again, the temperature of the surrounding room. And then it's E to the KT. K is your cooling rate. Okay, if the temperature is going down, then K is going to be negative. If the temperature is getting hotter, okay, then we have our K value is going to be positive. And then T is whatever time they're talking about. In our case, it's in minutes. Okay, so we take a look. Okay, and it says that pizza is baked at 100 degrees Celsius. Okay, so when it comes out, U sub zero is 100 degrees Celsius. Well, that's a hundo. Okay, and then allowed to cool at room temp where the temperature is 30 degrees Celsius. So room temperature, big T, is 30. If the temperature of the pizza is 80 degrees Celsius after 5 minutes, well, we can find the K value. So they give us T and U of T. So U of T we know is 80 degrees Celsius. It started at 100, and after 5 minutes it went down to 80 degrees. Well, now I can find my K value. So this is very similar to our last example. We got to find K, which is our cooling rate for this room temperature. So we go through, we do a little simplifying. Any questions on my setup? This is the temperature of the pizza after 5 minutes, surrounding room temp. Okay, again, this is in Celsius, so we must be in Europe. So here we go. First thing I would do is I would subtract the 30 over. That gives me 50. I would simplify here. 100 minus 30 is 70. And then e to the 5k. Look how nice and pretty that looks now. So when you look at this formula, it looks super scary, but it's very easy to simplify. We go through the process. We divide over. 50 divided by 70. I'm just going to simplify to 5/7. This guy cancels. And I have e to the 5k. Beautiful thing is we know how to solve this. We've been doing it 1,000 times now. Get up to that k, I got to step on a log. Use natural log, so the natural log of e cancels. So I get the natural log of 5/7 equals 5k. Natural log of e is 1, so we don't need it. Divide by 5. Here we go. And now my cooling rate, type it in. Natural log of 5 divided by 7, close it, and then divide by 5. And I get negative 0.0673. This is the cooling rate for this room. Okay, and now I can use this to answer the next question, or answer the first question. So the next question is, at what time can you begin eating the pizza if you want its temperature to be 50 degrees Celsius? So now, at what time, that's t equals question mark. So I use my formula. U of t, this is U of t right here, is 50. So that guy's 50. Big T is 30. The initial amount of the pizza right out of the oven was 100 degrees Celsius. Minus big T, e to the k. That's where I plug this guy in. and then t. And now it's pretty much set up the same way. You go through the solve, subtract 30, 100 minus 30 is 70, e to the k. So the next step we would take is we would divide by 70 here. And we got 2/7. 20 divided by 70 is 2/7. This guy cancels. And I've got e to the negative 0.0673 t power. From there, we always say, hey, you can't reach that t unless I step on a log. So I step on a log. A natural log is perfect. Bring that guy down. Now I'm running out of room, so I'm going to write here, I've got the natural log of 2/7 equals negative 0.0673 t. And now the last thing is just divide over negative 0.0673 and throw that in the calc. So calculator says, let's see what we got. Natural log 2/7, close it, and then divided by negative 0.0673. Press enter, and I get about 18.6 minutes. Seems like a long time to eat a pizza. Okay, so it takes about 18.6 minutes. Okay. In terms of part B, I really wouldn't worry too much about this one, but it says use a graphing utility to graph the relation between temperature and time. That's just hey, let's throw this in the calc. Okay, so we can do that pretty easily. So instead of u of t, I'm just going to do y equals, and then I've got my equation. The big T was 30 plus 100 minus 30 is, I'm going to make that 70. And then I have e to the negative 0.0673 x power. Okay, so this is what I'm going to put in for y1. So this is kind of neat when you throw it in the calc. So I'm going to go to y equals. I'm going to throw this in to y1. So I've got 30 plus 70 e, so second natural log, to the negative 0.0673 x power. Get it so you can see it here without the glare. So again, 30 plus 70 e to the negative 0.0673 x power. So instead of t, I'm using x. Okay. And it says using the intersect, determine the time. So find out what x is that needs to elapse before the pizza is 70 degrees Celsius. So that would be my y2. So I would have y2 is 70. So that's going to be a horizontal line, and I'm going to find out where those guys intersect. So I'm going to start in zoom 6, zoom standard. I know I'm not going to see this because this only goes up to 10, and I've got to get up to at least 70. So zoom 6, don't see it. So then I usually use zoom fit. So zoom 0. So I try zoom fit and see what kind of graph I get here. Okay, so this is, again, my cooling of the pizza. It's going down. And then I should see a horizontal line going across. That's 70. And now I want to find that intersection. So I tried zoom 6. I knew that was not going to work. So then I do zoom fit. So second trace, intersect. First curve enter, second curve enter, guess. And it takes about 8.3 minutes at the intersection. So it comes out piping hot at 100 degrees Celsius. And then how long does it take to get to 70 degrees Celsius? Well, it takes about 8.3 minutes. Okay. Says here, trace the function for large values of x's over time, and what do you notice about the temperature? So the trace is just going up here and pressing trace, okay? And then look at over time. So as the x value gets bigger, what's happening to the y value? So I keep going, and it's going down, right? It's getting to 64, 60, just keeps going down and down and down. Well, think about what's going on in this picture. Okay, the numbers are getting lower and lower. You have a slice of pizza, Or you have a big old pizza and it's been sitting out for 22 minutes. Okay, well, what happens when it gets to 25 minutes? It's going down, and it keeps going, and it's down to 40. So look at the temperature of the pizza now after 30 minutes. Okay, well, as I keep going for large values of x's, keeps going and going and going. Now we're at 35 degrees. So after about 38 minutes, it's down to 35. Well, let's keep going. 45 minutes or it's 33. Okay. The temperature still keeps going down. Well, as you keep on going and going and going, you'll see over time, as that x value is getting larger and larger, it's starting to approach a certain number. Okay, well, what is this number approaching? Think about what's going on. The pizza's been sitting out for almost an hour now. Okay, well, guess what it's at? Almost down to 30, almost down to big T. Okay, it's going to eventually get down to room temperature and get to 30. Okay, so that's the idea of the trace function for part D, getting down to 30. So room temperature is 30 degrees Celsius. So as X gets bigger and bigger, your temperature is getting all the way down to 30. Okay, and that should make sense. If you have something out, from the oven, it's eventually going to be as warm as what it's sitting in. Okay, so if it's sitting in the freezer, it's going to be frozen. Okay, if it's sitting out on the counter, well, it's going to be whatever room temperature is. And that's the idea. Okay. All right, ladies and gentlemen, that is it. That's all I got for today for chapter 5.8.